how long it takes to reach each planet. We live on a planet hurtling through the void at 67,000 miles per hour. Yet reaching our nearest neighbor takes months. The farthest worlds demand over a decade. Space travel isn't about distance. It's about velocity, gravity, and the unforgiving mathematics of orbital mechanics. This is the story of how long it actually takes to reach every planet in our solar system, from Venus at 1 month to Neptune at 12 years. Venus. Venus floats just 38 million miles away at its closest approach. Logic suggests a quick journey, weeks at most. But space defies simple logic. NASA's Mariner 2 required 3.5 months to reach Venus in 1962, and that mission revolutionized our understanding of our sister world. It detected the solar wind for the first time and measured surface temperatures hot enough to melt lead. Here's what makes Venus so challenging. Earth orbits at 67,000 miles per hour, while Venus races even faster at 78,000. You're not simply crossing 38 million miles. You're intercepting a target moving at breakneck speed while you yourself hurtle through space. It's like throwing a ball to someone on a speeding train while standing on another train traveling in a different direction. Modern spacecraft need roughly 32 days minimum to reach Venus using current technology. Even the Parker Solar Probe, one of our fastest vehicles ever built, requires meticulous trajectory planning. Engineers must calculate launch windows when Earth and Venus align properly. Miss that window and you wait months for another chance. The journey involves more than speed. Spacecraft must decelerate enough to be captured by Venus's gravity, or they simply fly past into deep space. Chemical rockets can only carry limited fuel. Every ounce matters. Every calculation must be perfect. The margin for error approaches zero. What makes Venus missions particularly brutal is the environment. As spacecraft approach, solar radiation intensifies. Venus itself radiates scorching temperatures from its thick atmosphere of sulfuric acid clouds. The surface pressure equals being half a mile underwater on Earth. Soviet Venera landers survived barely 2 hours before the planet destroyed them. Those precious minutes gave us images of a hellish landscape. Flat rocks, orange sky, crushing silence, then nothing. This 32-day journey represents our best case using chemical propulsion. Future nuclear thermal rockets could potentially reduce the trip to under 3 weeks, but that technology remains years away. Understanding Venus matters more than you might think. This planet started like Earth, similar size, composition, distance from the Sun. Yet somewhere in its history, Venus transformed into an inferno. Learning what went wrong there helps us understand what could happen here. Mercury. Mercury orbits just 36 million miles from the Sun. At its closest approach to Earth, the distance shrinks to 48 million miles. Logic suggests this tiny world should be easier to reach than Venus. Logic is catastrophically wrong. Messenger launched in August 2004 and finally entered Mercury's orbit in March 2011. 6.5 years to reach a planet closer than Mars. This seems impossible until you understand the nightmare of orbital mechanics. Mercury screams around the Sun. At 107,000 miles per hour, the fastest planet in our solar system. Catching up is hard enough. Slowing down enough to enter orbit is nearly impossible. The Sun's gravity well is incredibly deep. As spacecraft fall toward the inner solar system, they accelerate constantly. By the time you reach Mercury's orbit, your velocity is enormous. Too fast to stop, too fast to turn around. Chemical rockets simply cannot carry enough fuel to break against that gravitational monster. Messenger solved this with a brilliant but time-consuming trick. The spacecraft performed 1 Earth flyby, 2 Venus flybys, and 3 Mercury flybys before finally achieving orbit. Each flyby used planetary gravity to adjust speed and trajectory. The probe essentially spiraled inward over 6 years, bleeding off velocity bit by bit. The journey covered nearly 5 billion miles, despite Mercury being relatively nearby. Engineers calculated every maneuver years in advance. One mistake would have sent Messenger into the Sun or out into deep space. During those 3 Mercury flybys, before orbit insertion, the probe collected incredible data. It photographed 95% of the surface and discovered water ice in permanently shadowed craters near the poles. Water on the closest planet to the Sun, this discovery changed everything we thought we knew about Mercury. Bepi Colombo launched in October 2018 and won't reach Mercury orbit until December 2025. 7 years. Even with modern technology, Mercury remains brutally difficult to reach. Engineers say it actually takes more energy to reach Mercury than Pluto. The tyranny of the sun's gravity well makes the closest planet the hardest target. This counterintuitive reality teaches us something profound. In space, distance means less than velocity and gravity. The easiest targets aren't always the closest ones. Mars. Mars glows red in our night sky. At closest approach, it sits 34 million miles away. Yet every Mars mission takes 6 to 9 months using current chemical propulsion. NASA's Perseverance rover launched the 30th of July 2020 and landed the 18th of February 2021, 7 months of cruise through the void. But this isn't the worst part. Launch windows to Mars only open every 26 months. Miss your window, and you wait over 2 years for another chance. This happens because Earth and Mars orbit the Sun at different speeds. The cruise phase is deceptively dangerous. Spacecraft coast through interplanetary space at roughly 24,000 miles per hour. Engineers monitor systems constantly, performing attitude corrections to keep antennas pointed at Earth and solar panels aimed at the Sunday. Communication delays stretch to 20 minutes one way when Mars is distant. If something breaks, the spacecraft must fix itself before ground control even knows there's a problem. Radiation bombardment continues non-stop. Cosmic rays slam through the hull. Solar flares erupt, unpredictably. Every particle poses risk to sensitive electronics. Astronauts would absorb dangerous radiation doses during a 7-month journey, roughly 300 millisieverts, significantly increasing cancer risk. Entry, descent, and landing is the most terrifying part. This 7-minute sequence hits Mars's atmosphere at 12,000 miles per hour and must slow to 0. Everything happens too fast for human control. Perseverance used a sky crane system, a hovering platform that lowered the rover on cables to the surface. The maneuver worked flawlessly, captured on cameras for the first time in history. Current Mars missions use chemical rockets exclusively. The 7-month travel time is optimized through decades of refinement. But 7 months is brutally long for human missions. NASA aims to send astronauts to Mars in the 2030 seconds. Those crews would spend 7 months traveling there, over a year, on the surface waiting for proper return alignment, then 7 months coming home. Nearly 3 years total a duration that pushes human endurance to its limits. Mars might harbor evidence of ancient life. The planet once had liquid water. Rivers carved valleys. Lakes filled basins. Then, something changed. Understanding why Mars died could teach us how to keep Earth alive. Pluto, the 19th of January, 2006. A rocket lifted off from Cape Canaveral, carrying New Horizons. A probe the size of a grand piano, weighing just 1,054 pounds. It was heading to Pluto, and it was in a hurry. New Horizons left Earth faster than any spacecraft, before at 36,000 miles per hour right out of the gate. The International Space Station orbits at 17,000 miles per hour. This probe was moving twice that fast from launch. Pluto sits roughly 3 billion miles from Earth when closest. Using conventional cruise speeds, the journey would take decades. The team needed a different approach. The spacecraft carried minimal fuel. Most of its mass was scientific instruments, communications equipment, and power systems. It used a radioisotope thermoelectric generator for electricity. Solar panels would be useless in the outer solar system where sunlight is 1,000 times weaker than at Earth. New Horizons reached the Moon's orbit in just 9 hours. Apollo astronauts took 3 days to cover the same distance. The probe flew past Jupiter 13 months after launch, and this wasn't just a science opportunity. Jupiter provided a gravity assist that boosted New Horizons to 51,000 miles per hour, 14 miles every second. Even with that incredible speed, the journey to Pluto took 9.5 years. The probe spent most of that time in hibernation mode to preserve systems. Engineers woke it periodically to check instruments and make course corrections. Tiny trajectory errors early would become massive misses later. The 14th of July 2015, New Horizons screamed past Pluto at 30,000 miles per hour. The flyby lasted just minutes. Every instrument fired simultaneously. Then, it was over. The spacecraft couldn't slow down, couldn't orbit, couldn't return. It carried all that velocity from launch, gravity assists, and years of falling toward the outer solar system. New Horizons transmitted data back to Earth for 16 months after the encounter. The signals took 4.5 hours to arrive at light speed, but the images were worth it. Pluto revealed itself as a geologically active world with mountains made of water, ice, glaciers of frozen nitrogen, and possible subsurface oceans. This wasn't a dead frozen rock. Something generates heat inside Pluto. Something drives surface changes. The mission proved you can reach the outer solar system within a human lifetime. 9.5 years is long, but not impossible. Currently, the probe is over 5 billion miles from Earth, continuing to explore the Kuiper Belt. It will operate until roughly 2035 when its plutonium runs too low. The gravity assist revolution. Mariner 10 was about to attempt something never done before. The probe would fly close to Venus, steal some of its orbital energy, and redirect toward Mercury. If it worked, interplanetary travel would never be the same. The maneuver is called a gravity assist, or a gravitational slingshot. Imagine a spacecraft approaching a planet. The planet is moving through space at enormous speed. As the probe falls toward the planet, it accelerates. The spacecraft whips around and emerges on the other side, traveling faster than it arrived. It essentially steals momentum from the planet. The planet slows down infinitesimally. The probe speeds up significantly. Energy is conserved, but from the spacecraft's perspective, it gained velocity for free. No fuel burned, no engines fired. Voyager 1 and 2 elevated gravity assists to an art form. The twin probes launched in 1977 during a rare planetary alignment that happens once every 176 years. Jupiter, Saturn, Uranus, and Neptune lined up perfectly. A spacecraft could visit all four using gravity assists at each planet. Voyager 2 flew past Jupiter in July 1979. The encounter boosted its speed and bent its trajectory toward Saturn. It reached Saturn in August 1981, where another gravity assist redirected it to Uranus. Then Uranus sent it toward Neptune. The probe visited 4 giant planets in 12 years. Without gravity assists, the journey would have taken decades longer and required impossibly large fuel loads. The math behind gravity assists is extraordinarily complex. Engineers must calculate approach angle, altitude, velocity, and timing with extreme precision. Miss by a few miles, and the maneuver fails. The margin for error is razor thin. What gravity assists taught us is profound. Space isn't empty. Planets are resources. Their motion and mass can be harnessed. Orbital mechanics isn't about fighting gravity. It's about using gravity as a tool. Dance with the planets correctly, and they'll throw you across the solar system. Jupiter. Jupiter dominates our solar system in ways most people never realize. This gas giant contains more mass than all other planets combined. Its gravity well extends millions of miles into space, and every mission to the outer planets uses Jupiter as a mandatory stop. Pioneer 10 arrived at Jupiter in December 1973. The encounter accelerated the probe enough to escape the solar system entirely. Jupiter made that possible. Voyager 1 reached Jupiter in March 1979. The close flyby boosted its velocity by 35,000 miles per hour, nearly 10 miles every second, gained essentially for free. Without Jupiter, Voyager 1 would still be crawling through space somewhere beyond Mars. Galileo's spacecraft spent 6 years reaching Jupiter and arrived in December 1995 to enter orbit, the first probe to orbit the gas giant instead of just flying past. Galileo studied Jupiter for 8 years, discovering subsurface oceans on Europa and watching comet Shoemaker-Levy 9 crash into Jupiter's atmosphere. New Horizons screamed past Jupiter 13 months after launch. The flyby boosted the probe past 50,000 miles per hour, enabling it to reach Pluto in 9.5 years instead of decades. Jupiter literally saved years of travel time. Why is Jupiter so useful? The numbers tell the story. Jupiter orbits the Sun at 29,000 miles per hour. When a spacecraft approaches from behind in the same direction the planet moves, it can gain enormous velocity. The transfer of momentum from Jupiter to the tiny probe is negligible to Jupiter but massive for the spacecraft. Jupiter's gravity well extends roughly 32 million miles into space. Inside this region, Jupiter's gravity dominates. Spacecraft can be captured, redirected, or accelerated depending on their trajectory. Mission planners use this region like a cosmic intersection, enter from one direction, leave going another, always faster than you arrived. The radiation around Jupiter is brutal. The planet's magnetic field traps charged particles that form radiation belts far more intense than Earth's Van Allen belts. Electronics must be heavily shielded. Even so, systems gradually degrade. Jupiter is the gateway to the outer solar system. No mission to Saturn, Uranus, Neptune, or beyond skips Jupiter. The planet is mandatory. Its gravity is too useful. Its position too perfect. Saturn. Saturn floats roughly 886 million miles from the Sun. Reaching those magnificent rings requires commitment measured in presidential terms. Pioneer 11 reached Saturn in September 1979 after 6.5 years of travel, having used Jupiter's gravity 16 months earlier to redirect toward the ring giant. Voyager 1 arrived in November 1980, 16 months after leaving Jupiter. The flyby revealed active weather systems, lightning storms bigger than Earth, wind speeds of 1,000 miles per hour. Titan had a thick nitrogen atmosphere. Enceladus had geysers shooting ice into space. But Cassini changed everything. This massive probe launched in October 1997 and took 7 years to reach Saturn, arriving in July 2004. The journey was indirect. Cassini flew past Venus twice, Earth once, then Jupiter. Each gravity assist adjusted trajectory and built velocity. Without these maneuvers, Cassini couldn't have carried enough fuel to reach Saturn and enter orbit. Orbit insertion around Saturn required extraordinary precision. The probe approached at 72,000 miles per hour and fired its main engine for 96 minutes straight, consuming tons of propellant. If the engine had failed, Cassini would have flown past and been lost forever. The mission lasted 13 years in Saturn orbit. Cassini completed 294 orbits and flew past Titan 127 times. Each Titan flyby was a mini-gravity assist that reshaped Cassini's orbit, allowing engineers to visit different parts of the Saturn system without burning precious fuel. Cassini discovered oceans beneath the ice of Enceladus. The moon shoots geysers containing organic molecules, liquid water, organic chemistry, and energy sources mean Enceladus might harbor life. This tiny moon became one of the most important discoveries in planetary science. In September 2017, mission controllers crashed Cassini into Saturn. The probe was running low on fuel and could no longer maintain stable orbit. Rather than risk contaminating potentially habitable moons, they sent it to burn up in Saturn's atmosphere. Cassini transmitted data until the very end. The 7-year journey to reach Saturn represents a practical minimum using current technology. Engineers can't significantly improve on this timeline without radically new propulsion. Beautiful things take time to reach, and every mission to Saturn has revolutionized our understanding of the outer solar system. Neptune, the 20th of August 1977. Voyager 2 lifted off from Cape Canaveral with a destination that seemed almost impossible. Neptune. Expected arrival, August 1989, 12 years. Neptune orbits 2.8 billion miles from the Sun, invisible to the naked eye. No spacecraft had ever visited. Voyager 2 would be the first, and remains the only probe to fly past Neptune up close. The journey took advantage of a once-in-a-lifetime planetary alignment. Jupiter, Saturn, Uranus, and Neptune arrange themselves in a cosmic straight line, a configuration that occurs every 176 years. Voyager 2's trajectory was meticulously planned to visit all four. The probe reached Jupiter in July 1979, 2 years after launch. Jupiter's gravity provided the first major boost. Voyager 2 continued towards Saturn, arriving in August 1981, 4 years into the mission. Saturn's gravity assist sent the probe toward Uranus, which it reached in January 1986, 8.5 years into the journey. Uranus's gravity flung Voyager 2 toward Neptune. The final leg took 3 more years. Every day carried the probe farther from Earth. Communications required over 4 hours, one way, at light speed. If something broke, the spacecraft had to diagnose and fix itself before ground controllers could even respond. Neptune appeared as a brilliant blue world. Methane in the atmosphere absorbs red light, reflecting only blue. Wind speeds at Neptune reach 1,200 miles per hour. The fastest winds in the entire solar system blow on this frozen giant, so far from the Sunday. Voyager 2 discovered Neptune's Great Dark Spot, a storm system larger than Earth. The probe also found 6 previously unknown moons. Neptune's largest moon, Triton, became the mission's grand finale. Triton orbits Neptune backward. This retrograde motion suggests it was captured from the Kuiper Belt billions of years ago. The most shocking discovery was Triton's geysers. Active geysers, shooting nitrogen gas 5 miles high, on a world that's minus 390 degrees Fahrenheit. This frozen moon somehow has geological activity. The Neptune flyby lasted just hours. Voyager 2 couldn't slow down, couldn't orbit. It raced past at 38,000 miles per hour. Every instrument fired simultaneously, then Neptune shrank to a point of light and disappeared. Voyager 2 continues outward. It's currently over 14 billion miles from Earth, still communicating, still sending data. Mission controllers expect communications to continue until roughly 2025, when power drops too low. 12 years to reach Neptune. 12 years of waiting, 12 years of hoping. Nothing would break. The spacecraft survived and completed the grand tour 4 planets visited. Dozens of moons discovered, thousands of images transmitted. The mission succeeded beyond anyone's dreams. No spacecraft has visited Neptune since. No missions are planned. If a probe launched today, it would arrive in the late 2030s, over a decade away. Neptune remains profoundly unexplored. The nuclear future. The travel times we've explored: 32 days to Venus, 7 months to Mars, 7 years to Saturn, 12 years to Neptune. These aren't just statistics. They're the boundaries of human expansion, the limits that define what's possible. But there's hope on the horizon. Nuclear thermal propulsion could revolutionize space travel. Instead of burning chemical fuel, a nuclear reactor heats liquid hydrogen to extreme temperatures. The hydrogen expands and shoots through a nozzle, achieving exhaust velocities double what chemical rockets produce. This means double the efficiency, half the fuel mass, and dramatically faster trips. The concept isn't new. Between 1955 and 1973, NASA built and tested 20 nuclear thermal rocket engines. They worked brilliantly, producing incredible thrust with specific impulses, reaching 900 seconds, triple the performance of chemical systems. Political concerns killed those programs, but the physics was proven. Modern designs use low-enriched uranium that can't be weaponized. The reactor remains inactive during launch and only turns on in orbit. If the rocket crashes on the launch pad, radioactive material stays contained. A nuclear thermal rocket could accelerate a Mars-bound spacecraft to much higher velocities than chemical systems. The journey could shrink to 6 weeks instead of 7 months. Astronauts spend less time in radiation, less time in microgravity, less time psychologically isolated. Everything improves. The Draco program, demonstration rocket for agile cislunar operations, aims to demonstrate this technology by 2027. The project will launch a nuclear thermal rocket, test it in orbit, and prove the concept works. If Draco succeeds, operational systems could fly by the mid-2030s. Mars missions would use nuclear thermal propulsion with journey times cut in half or better. Beyond nuclear thermal propulsion lies nuclear electric propulsion, an even more efficient system where a reactor generates electricity to power ion drives. The combination offers specific impulses of 5,000 seconds or more, 10 times better than chemical rockets. The thrust is low, but acceleration continues constantly for months or years. Velocity accumulates until the spacecraft is moving incredibly fast. NASA estimates nuclear electric propulsion could reduce Mars round trips to roughly 2 years total. Less radiation exposure, shorter time in microgravity, better crew health, more flexible launch windows. The reactor must be larger than nuclear thermal systems, but the superior propulsion efficiency compensates. And on the distant horizon lies fusion propulsion. If we could harness the power that's driven the sun for 4.6 billion years, interplanetary travel would transform completely. Fusion rockets would exhaust plasma at thousands of miles per second, with specific impulses reaching tens of thousands of seconds, 50 times better than nuclear thermal, 100 times better than chemical rockets. Jupiter in 2 months instead of 5 years. Saturn in 4 months instead of 7 years. Neptune in 1 year instead of 12. Pluto in 18 months instead of 9 years. Outer planet missions would shrink from decades to months. The challenge is making fusion work. Ground-based fusion reactors are still experimental. Space fusion reactors must be smaller, lighter, more efficient. But research continues, and results are promising. Within this century, fusion propulsion might become reality. The human frontier. These advances in propulsion aren't just about convenience or cost. They're about survival. Humanity needs options. Earth won't remain habitable forever. Shorter-term threats are more pressing: asteroid impacts, supervolcanoes, nuclear war, engineered pandemics, climate change. A multiplanetary species survives catastrophes. A single-planet species risks extinction. The travel times to potential refuge worlds determine whether expansion is practical. Mars is the obvious first colony close enough to resupply, with a similar day-night cycle, available water, and potential for in-situ resource utilization. But 7-month travel times constrain development. Nuclear propulsion cuts Mars travel to 45 to 90 days. Supplies arrive faster. Emergency evacuation becomes possible. The psychological burden decreases. Mars starts feeling like a distant territory rather than an alien world. Fusion propulsion could reduce Mars trips to weeks. At that point, Mars resembles Antarctica, remote and harsh, but accessible. Research stations become permanent settlements. Industrial development becomes economic. Mars transitions from experiment to viable colony. The asteroid belt contains enormous resources, with total mass exceeding Earth's. Mining asteroids could provide materials for space-based industry. Building spacecraft in space avoids Earth's gravity well, making exploration cheaper and more sustainable. But reaching asteroids takes years with current technology. Nuclear electric propulsion could cut this to months, making asteroid mining economically viable. Jupiter's moons represent the next frontier. Europa has subsurface oceans and possibly life. Ganymede is the largest moon in the solar system. With fusion propulsion, Jupiter missions take months instead of years. Shielded habitats on the moons could house research bases. The Jovian system becomes accessible. Saturn's moons offer unique opportunities. Titan has liquid methane lakes, a thick atmosphere, and organic chemistry everywhere. Enceladus has subsurface oceans venting into space. Advanced propulsion extends humanity's reach to Saturn within reasonable timescales. The decisions we make in the next few decades matter. Investing in propulsion technology today enables expansion tomorrow. Failing to invest traps us on Earth, leaves us vulnerable, limits our potential. Right now, humanity stands at a threshold. We have robots exploring every planet. We have plans for Mars missions. We're developing nuclear propulsion. The pieces are assembling, but success isn't guaranteed. If we succeed, humanity spreads across the solar system. Mars cities, asteroid mines, Jupiter bases, a multi-world civilization resilient to catastrophe. This future is possible. The physics allows it. The technology is developing. We know how long it takes to reach each planet. Now we must decide whether to go. The journey of 1,000 worlds begins with a single launch. The cosmos awaits, and our window to step through it may not remain open forever.